Okay, Ollie, let's try to make sense of these notes on determining linear maps. The professor just went through this section pretty quickly.
Yeah, I'm a little lost. The title is Determining Linear Maps. So what does that even mean?
Well, let's look at the first real slide, page 2. It asks a pretty important question. It says, let V and W be vector spaces over a field F. Then it asks, what information do we need to know to define a linear map, F, from V to W completely?
I guess you need to know what the map does, right? Like where it sends every single vector in V?
Exactly. But think about that for a second. If V is something like R3, there are infinitely many vectors. We can't list them all. There has to be a more efficient way.
Oh, I see the problem. So we need some kind of shortcut?
Right, and the notes are hinting at a solution by bringing up something we've already learned. Look at the next page.
Review. What is a basis?
Correct. It reminds us that a basis is a set of vectors that's linearly independent and generates the entire vector space. And if we have a basis, say v1, v2, v3, all the way to vn, any vector v in V can be expressed as a unique linear combination of those basis vectors.
Wait, unique? What's important about that?
That's key. It means that for any vector v, there's only one way to write it as v equals b1 v1 plus b2 v2 plus all the way to bn vn. The coefficients bj are a unique set of scalars for that specific vector v.
Okay, so how does that help us with the linear map?
The next page shows us the trivial part. If we already have a linear map and we know what it does to the basis vectors, f of v1, f of v2, all the way to f of vn, then we can determine what it does to any vector v.
Oh, because f of v is just a linear combination of the images of the basis vectors. So f of v equals b1 f of v1 plus b2 f of v2 plus f of vn.
Perfect! The notes put it exactly that way. It's because of the properties of a linear map. That's the easy part. But now for the core question at the bottom of the page.
Is the converse true? What does that mean again?
It's asking, if we start with a set of vectors in W, can we define a linear map, F, that sends the basis vectors of V to those specific vectors in W? And if so, is that map the only one that does it?
And the notes say yes. Theorem 1 confirms it. For any set of n vectors in W, W1, W2, Wn, there exists a unique linear map F from V to W such that Wj equals f of Vj for each j from 1 to n.
Yep, it says that if we just decide where the basis vectors go, that's enough to define a unique linear map. The little diagram on the page helps to visualize it, showing the connections between the vectors in V and W.
Okay, so the proof starts with step 1, we construct the map. It seems to be building the map exactly how we just said it works. It takes an arbitrary vector v, expresses it as a unique linear combination, and then defines f of v using those same coefficients on the new vectors in W.
Right, so f of v equals b1 w1 plus b2 w2. That's how we're defining this new map. Now we have to prove that this map is actually linear and that it's unique.
Step 2 is to show that it's a linear map. Okay, so we have to prove two things, right? The vector addition property and the scalar multiplication property.
Exactly. The notes show the vector addition part first. They take two vectors, v and v prime, express them in terms of the basis, and then define f of v prime, and f of v plus v prime.
Oh, I see. The coefficients for v plus v prime are just the sums of the coefficients of v and v prime. So when we apply the definition of our new map F, we get f of v plus v prime equals b1 plus b1 prime w1 plus
bn plus bn prime wn, that's the same as f of v plus f of v prime. It works.
Now for scalar multiplication. The notes say for any vector v and for any scalar a from the field F, we have AV equals AB1 V1 plus ABN Vn. When we apply our definition of F to AV, what do we get?
We get f of AV equals AB1 W1 plus ABN Wn, and we can factor out the scalar a, so that's equal to a times B1 W1 plus Bn Wn, which is just a f of v. It works. So F is definitely a linear map.
Awesome. And now for the last part of the proof, step 3, which is about uniqueness. The notes ask us to suppose there's another linear map, let's call it G, that also sends each basis vector Vj to the same vector Wj.
So we're assuming G of Vj equals Wj for every j, and we have to show that G must be the same as our map, F.
That's the plan. The notes take an arbitrary vector v and express it as a linear combination of the basis vectors. Then they show us what G of v looks like.
Let's see. G of v equals G of B1 V1 plus Bn Vn. And since G is a linear map, we can pull out the coefficients and separate the sum. So that's B1G of V1 plus BNG of Vn.
And what's G of Vj equal to?
We just assume that G of Vj equals Wj, so we can substitute that in. G of V equals B1 W1 plus Bn Wn. Wait a second. That's exactly the same definition we used for f of v.
Bingo! Since G of v is equal to f of v for any vector v in the space, the maps must be identical. Therefore, our map F is unique.
So, to summarize what we just proved, to define a linear map, all we need to know is where the basis vectors go. And that gives us one and only one linear map.
You got it. And the rest of the notes apply this idea to matrices, which is what we were doing in class yesterday. They're reviewing the idea of an elementary vector, EJ, which is just a vector with a 1 in the jth position and everything else is 0. That set of vectors, E1 all the way to En, is the standard basis for f to the n.
And then it defines a linear map FA, that's a multiplication by an m by n matrix A. It also shows that f of AJ is just the jth column of the matrix A.
Right, and that leads to the final theorem.
Theorem 2. For any linear map f of Fn to Fm, there exists a unique m by n matrix A such that f equals Fa.
See? It's the same core idea, but now it's about matrices. It says that for any linear map between these two specific vector spaces, you can always find one, and only one, matrix that represents that map.
And the proof for that uses Theorem 1. It says, let's define our matrix A by making its columns the images of the standard basis vectors. So A is the matrix where the jth column is f of EJ. Then we know that f of AJ is also the jth column of A, so f of A and f do the same thing to the basis vectors, and by Theorem 1, they must be the same map.
Exactly. And since the columns of A are completely determined by what f does to the basis vectors, the matrix A itself is unique. That's a powerful connection between linear maps and matrices.
Wow, okay. I think I actually get it now. Thanks, Anna. I feel a lot better about this.
No problem. I'm glad we could figure it out together. This definitely makes the homework a lot less scary now.
For sure. It's so much easier when you understand the why behind the theorems.
Ready to tackle the problem set?
You bet. Let's do it.